A typical optimization model development cycle starts with the scope definition in business terms. Next, the OR analyst uses a scoping document to identify the objectives, decision variables, and constraints in order to construct a mathematical optimization model. The OR analyst will also gather data to populate the model and then create and test a prototype with a small data set. The model is then edited as required based on the test results. Next, the OR analyst creates and tests a complete instance of the model and evaluates the performance. The model is adjusted as needed, and advanced solution techniques developed if required in order to find a good solution in reasonable time. The objective function of an optimization model is a mathematical representation of the business objectives or goals to be achieved. Objective functions always start with the words maximize or minimize, and can be either a simple expression involving a single business objective or a more complex expression combining several business objectives. Some examples of objectives are to maximize profit, minimize cost, minimize tardiness, and maximize customer service. Decision variables in an optimization model represent values or decisions that are determined by the solver engine in order to arrive at the best possible value of the objective function. Examples of decision variables are how much of a given product to produce, how many people to hire for a given task, which location to choose for a new warehouse, etc. The values of the decision variables are determined during the solution process. These values are usually unknown in a model, although it's possible to provide initial guess to help optimization. Decision variables have a domain, the set of all possible values for the variable, bounds, the lower and upper limits of the domain, infinite bounds are allowed, a type, for instance, real, integer, Boolean, or interval. It is important to choose the decision variables well because they impact the formulation of the constraints and the solution method used. Constraints define the relationships between different decision variables and also relate the data to the decision variables. They represent the limits within which the solution should exist. Examples of constraints are that the amount produced of a given product should be less than the production capacity, that the people hired for a given task should have a minimum set of skills, that the total cost of building a new warehouse should be less than the budgeted amount, etc. Constraints are either hard or soft. Hard constraints should not be violated under any circumstances. For example, a constraint on production capacity when no additional capacity is available by any means. Soft constraints can be violated under certain circumstances. In the case of soft constraints, a penalty is often added to the objective to minimize the constraint violation. IBM iLog CPLEX Optimizer is a solver engine for mathematical programming problems and includes the simplex, barrier, and mixed integer algorithms that are used to solve linear, mixed integer, and some quadratic programming problems. IBM also offers CP Optimizer for solving constraint programming problems. CPLEX can automatically choose the most appropriate solution algorithm for a particular problem based on the problem structure. It is also possible to have more control over the algorithm by setting some parameters or by developing custom algorithms. In optimization, a solution is a proposal of specific values for the decision variables, regardless of whether it is a desirable or even an allowable set of choices. Solutions can be classified as follows. A feasible solution is one that satisfies all the constraints. An optimal solution is a feasible solution that also achieves the best possible value of the objective function. An infeasible solution is a solution where one or more constraints are violated. An unbounded solution is where the constraints are not completely described, resulting in an objective that goes to plus or minus infinity. The set of all feasible solutions is called the feasible region.